Okay, in this video we will finish talking about the work-energy relationship. We initially talked about how energy gets converted from initial to potential, right, or to final, or to kinetic to potential, but total mechanical energy always stays constant. And so, for example, we have a skier and it's skiing up a hill. As it skis up a hill, the skier will slow down, obviously, and in doing so loses kinetic energy. But since the skier is going up, that kinetic energy that's lost turns into potential because height increases. So high kinetic, low potential will equal low kinetic, high potential, and total mechanical energy is conserved. From the top of the hill on down, not very much kinetic, but a lot of potential. But as the skier goes down the hill, gains kinetic and loses potential. But overall, kinetic potential I start with equals kinetic potential I end with. Total mechanical energy is conserved. We were talking about conservative forces, like gravity in this case. A pendulum works the same way. So position 1, you have 6 joules of kinetic, right? And it's moving at 0 meters per second. But what's its height going to be? Well, we'll say the mass is 1 in this case, and 1 times g is 9.8, and then we can solve for our height. As we go down, we get to position 2. At position 2, we have equal potential and kinetic energy. It's gained speed to gain kinetic energy, but its potential has dropped down to 3. Its height is lowered, but its velocity is increased. At position 3, its height is 0, therefore potential energy is 0, kinetic energy is 6. Again, we just work backwards with math and we can find how fast it's going at the very bottom. And then we go back up to 4, where position 1 and position 4 will be exactly the same. The height will be the same because the potential energy is still 6 joules. But the energy total, mechanical, is still 6. And then we work to find the rest of the information. So as a coaster car loses height, it gains speed because potential energy is transformed into kinetic energy. As it gains height, it loses speed. Kinetic energy is then transformed into potential energy. But the totals of potential and kinetic energy at all 3 instances are still the same. Here's a roller coaster. Potential energy is at 40 at the top. At the very bottom, there's no potential. It's all turned into kinetic. And then we look at the loops that are involved. One loop has 20 and 20. One loop has 25 and 15. So at this loop here, you're traveling faster, right, because you have more kinetic energy, but you're also lower to the ground. So when we look at loops on a roller coaster, if they're not the initial drop, the higher the loop, the slower you're going to go through the loop, if you will. Here you have one of those humps that happens in the middle, and you can see your kinetic energy is at 32,005, which means you'll be going faster here than you will be at here or here. But you're also lower because your potential energy. At the very bottom, you're going full speed because you have no potential energy. Everything's kinetic. And then you'll see the paths here and here. Comparing these two, your kinetic energy is greater here, which means you'll be traveling faster on that hill than you will on this hill. But at the end, your potential plus kinetic always equals the same. In this case, 40,000 joules. The ski jump example we talked about in a previous video. Again, we can do the math. If we want to find the velocity or compare the velocities at any point, we know that here, no kinetic energy, no velocity here. 20,000 here, 20,000. The object is traveling at the same velocity. Here, the kinetic energy is higher, therefore traveling faster than at either one of these. But then at the very bottom, since there's no potential energy and all we have is kinetic, it is traveling its fastest. Much faster than it is here. But at the end of the day, total mechanical energy is still 50,000 joules. Another way to look at this is using bar charts. I'm going to give you a couple of equations here. We can look here. Kinetic energy plus potential energy that you start with plus the work that's used or added, right? It could be positive or negative, will equal the final kinetic plus potential energy. This is the main equation we use when we look at an energy situation. We can break it down even more and take our potential energy and convert it to gravity or spring, especially if we have a spring, motion, and gravity and height change all included. And of course, work that's being external. So we use this to analyze the initial and final states of the object. Okay, so we want to look at the different types of energy. We want to analyze forces. Remember, external forces do work, okay? And this work should be positive or negative. And so we use bars to do this, to show the various forms of energy. The exact height, not important, but the sum of the heights to the left must be the same as the sum of the heights on the right. So, for example, you got a ball on top of a stand, and it's not moving, okay? There's no springs, so it's at rest, no kinetic energy. It has height, therefore it has potential gravity, and there are no springs. And there's no external work being done, therefore all there is potential energy. So that's the bar I have filled. As the bar drops and right when it hits the ground, is it moving? Yes. So it has kinetic energy. Does it have height? No more. Nope. Does it have springs? Nope. Therefore all that's left is kinetic. So all my potential energy gets converted to kinetic energy. So here we have a car traveling to the right, and we got brakes that are doing some action there to slow us down. So let's look at initially. Car moving? Yes. Does it have height? No. Is there springs present? No. But there's going to be some negative work here, okay? There's going to be negative work. Now, at the end, the car is at rest, so there's no kinetic energy. The potential energy, there's no change in height, and there's no springs. So that means at the end, our final energy has nothing on there, okay? Which means our kinetic energy has to equal the external energy or the friction present. Since these two are going to be opposite, one's positive, one's negative, that equals 0 when you add them together, therefore no final energy at the end. Here we got an object here that's going from A to B, and what we have is we have kinetic energy, is the gear's at rest, so there's no kinetic energy. There's an elevated position, and there's no spring. So we have potential energy due to gravity. Okay. Now we have the poles doing some positive work. The poles are pushing the skier forward so they can go down the hill. So therefore, we're going to have some positive work external. Okay. So this is initial. Now, finally, when it goes from A to B, the skier is moving, so there's kinetic. There's a little bit of elevated position due to the height of the hill. There's no springs present. So we know that potential afterwards and kinetic afterwards. Right? So let's say this is 4 blocks high, right? Or 3 blocks high, and this is 1 block high. So it's 3 and 1. We know that these will have to equal 4 because we want 4 and 4. So we want everything to be equal at the end. So kinetic energy initial plus potential energy equals kinetic energy final plus potential energy final. So just some different things you can look at is that we know if I have all potential, then that's going to be my total mechanical energy. Kinetic plus potential equals total mechanical energy. Kinetic plus potential equals total mechanical energy. Kinetic plus potential is total mechanical energy. In this case, my total mechanical energy doesn't change, but my potential and kinetic do, just as long as they add up to the total at the end. So at A, we got all potential. At B, we got a combination of potential and kinetic. At C, going a little bit faster, so we have more kinetic than potential, but our total mechanical energy is still constant. At D, we're at the very bottom. There's no potential, therefore it's all kinetic. And at E, we have a little bit of height, so some of the potential energy takes the place of kinetic. But at the end, everything added together equals the same total mechanical energy. We can also look at speeds or heights. The higher the potential energy, the higher height. So A is higher, B is second highest, C is third highest, E is fourth highest, and D is fifth highest. Again, looking at potential energy. Looking at kinetic energy, we can find velocities. D is fastest. E is second fastest. Then we look at C and B. C is third fastest. B is fourth fastest. And of course, A is fifth fastest because you're not moving yet.